Welcome to the deep dive. This is where we really get into complex computer science topics using the key resources to make sense of it all. And today's session, it's tailored just for you.
That's right. We're diving into specific questions from the Cambridge International ASNA level Computer Science Paper 3, the Advanced Theory paper from October, November 2024.
Yep, we've got the question paper right here. Our mission is to really unpack each question, leave no stone unturned, make sure you get the concepts behind them.
Exactly. Think of it like your own personal study session. We're going deep.
I'm Ask Z.
And I'm the AI teaching assistant.
And we both assist Sir Zafar, Ali Khan, ZAK. Seriously, if you need the best A&O level computer science resources, you've got to check out cswithzak.com. It's fantastic.
Absolutely. So today we'll be covering, well, quite a range. Binary floating point, RSC processors, circuit switching.
.tc pip layers, hashing, set data types, Boolean logic, K-maps.
Memory management like segmentation and disk thrashing, OOP concepts.
And even BNF, syntax diagrams, and binary trees using linked lists and arrays. It's a packed session.
It is. So let's jump right into question one.
Okay, question one, binary floating point representation. Part A asks us to convert the denary number plus 201.125.
Right, into a binary floating point format using a 10-bit mantissa and a 6-bit exponent. And both need to be in 2's complement.
Okay, so plus 201.125. First things first, we need to get this into binary, right? Integer part and fractional part separately.
Exactly. Let's take the integer part, 201. We need to find the powers of 2. Let's say 128, yes. Plus 64, that's 192.
Okay, 192, we need 9 more. So add 8, that's 200.
Good. And then just add 1. So 128 plus 64 plus 8 plus 1.
Which in binary is 100, 1001. That's 8 bits.
Perfect. Now for the fractional part, 0.125. This was a bit easier usually.
Yeah, that's 18, isn't it? Which is 2 to the power of -3.
Precisely. So in binary, that's just 0.001.
Okay, so putting them together, we have 100, 1001.001.
Correct. Now the tricky part, we need to fit this into a 10-bit mantissa and a 6-bit exponent, both 2's complement. The number's positive, so the sign bit will be 0 eventually.
Right. We have 100, 1001.001. How do we position this for the mantissa?
Well, the standard way is to think about where the binary point needs to be. The value is 201.125. If we imagine the point right after the first bit, 1.100100101, we need...
Oh, hey, I think our listeners got something to say.
This is Zafar Ali Khan. Actually, we don't have to put the point in between first two ones. Rather, we will move the point towards all the way towards the left so that we could get 0.11001001 into 2 to power 8. That is what I want. You got me?
Absolutely, we've got you right here with us. Thanks for checking it. We were just tackling how to represent the number 201.125 in binary floating point.
Yes, we've converted it to binary as 1001.001. Now we're about to discuss fitting that into the 10-bit mantissa and 6-bit exponent format specified in the question.
Okay, so about that mantissa, it needs to be 10 bits. We have 1.100101001. Oh yeah,
Yeah, actually, I was telling that point should not be between first two ones. Rather, point should move towards the left all the way. So this would give us 0.11001001001 into 2 to power 8. Since the point would move 8 times towards the left, so the power of 2 would be 8.
Interesting way to think about it. You're suggesting normalizing. So the binary point is at the very beginning. Yes.
Okay, let's unpack this. So you're proposing 0.1100001001 and then multiplying by 2 to the power of 8 to get back to 201.125.
Exactly. Moving the binary point 8 places to the right from 0.1100101001 would indeed give us 111010101, which is 201.125 in binary.
And the exponent would then be 8. How would we represent 8 in our 6-bit 2's complement exponent?
Well, 8 in binary is 1000. Padded to 6 bits, it's 001,000. So in your suggested representation, the exponent would be 001,000.
Okay, so the mantissa would be the first 10 bits after your initial 0 and the binary point. 11101010. Notice we still have that last 1 from the fractional part that we'd have to truncate to fit into the 10-bit mantissa.
You're right. Regardless of whether we put the binary point after the first one or all the way to the left, with a 10-bit mantissa, we still face that limitation in precision due to the fixed size.
Here's where it gets really interesting. Both methods achieve a form of normalized representation, but the standard convention often places the binary point after the first significant one.
That's primarily for consistency across different floating point numbers, but your approach highlights the flexibility in how we can think about the mantissa and exponent relationship.
So what does this all mean? Even with your method, we still encounter that truncation. Thanks for bringing up that perspective. Now, let's get back to the standard approach for a moment.
Using the standard normalization, 1.10001001, we had exponent of 7 binary 00.
The answer should not be 1.1. Answer should be 0.11001010, and exponent should be 0.10000. So now move on to the question 1B.
Thanks for clarifying your thoughts. You're right. Looking at it with the normalized form, starting as 0.1100100100, and an exponent reflecting that shift.
Yes, if we take your normalized mantissa of 1111000100, remembering the implied leading 0 for positive numbers and 2's complement for the 10-bit mantissa, that fits perfectly.
And you suggested an exponent of 00100, which is indeed 8 engine decimal. So the representation you're proposing is a mantissa 1010101010 and an exponent of 001,000.
That's a valid way to represent it, focusing on shifting the point all the way to the left after the initial 0. Thanks for guiding us through your reasoning.
Absolutely. Now let's move on to part B of question 1.
Part B gives us a binary floating point number, mantissa 10101001 and exponent 000101. We need to convert this back to its denary value.
All right, let's tackle the exponent first. 000101. It's a 6-bit 2's complement number. The leading 0 means it's positive. And 101 in binary is 5 in denary. So the exponent is plus 5.
Excellent. Now for the mantissa, 10101010011. It's a 10-bit 2's complement number. Notice the leading 1.
That tells us it's a negative value.
Correct. To find its magnitude, we need to flip the bits and add 1. Flipping 101010000001. Adding 1 results in 0101000101.
Okay, 0101001101.
Let's convert that binary to denary. That's 256 plus 64 plus 8 plus 4 plus 1.
Exactly, which sums up to 333. So the magnitude represented by the mantissa is 333. Given it's a 10-bit mantissa, the binary point is considered to be after the first bit, making it a fraction. So the mantissa's value is effectively negative 333 divided by 2 to the power of 9, which is negative 333512, and the exponent is plus 5.
Precisely. So we take the mantissa's value and multiply it by 2 raised to the power of the exponent. There's 3333512, 25.
2 to the power of 5 is 32, so we can simplify that. 512 divided by 32 is 16, so we get negative 3316.
And negative 333 divided by 16 gives us negative 20.8125.
I got it. The denary value is negative 20.8125. It really highlights how the 2's complement and the exponent work together to represent signed and scaled numbers.
It does indeed. These are foundational concepts. Ready to move on to question 2, which is about RISC processors.
Absolutely. Let's dive into RISC, Reduced Instruction Set Computer. The name itself hints at the main idea, a focus on a smaller set of simpler instructions.
That's the core principle. So a primary feature of ZAK is a limited number of instruction formats. Instead of a wide array of complex instruction structures, RISC utilizes a concise and standardized set.
And what's the advantage of having fewer instruction formats?
It simplifies the instruction decoding process significantly. A simpler decoding unit can operate faster, often implemented using hardwired logic rather than slower microcode, which can be another characteristic of RISC architectures.
Okay, that makes sense. Simpler instructions, faster decoding. What's another key feature?
RISC processors are designed to execute most instructions within a single clock cycle. Because the instructions are streamlined, they can often be completed very quickly, ideally in just one tick of the processor's internal clock.
That would definitely lead to higher overall processing speed and efficiency. What's the third feature we should consider?
Fixed length instructions are another hallmark of RISC. In contrast to CISC, complex instruction set computers, where instructions can vary considerably in length, RISC instructions all occupy the same number of bits.
Why is having fixed length instructions beneficial?
It simplifies the process of fetching instructions from memory. More importantly, it makes instruction pipelining much more effective. Pipelining allows the processor to work on multiple instructions in different stages of execution simultaneously, and fixed length instructions make managing this parallel processing much smoother.
Got it. So fixed length aids in efficient instruction handling and pipelining. And a fourth key feature of RSC.
A large number of general purpose registers is crucial in RSD design. RSC architectures rely heavily on these registers to hold data that's being actively processed. Data is loaded from memory into registers, operations are performed on the data within the registers, and the results are then stored back to memory if needed. This minimizes the slower accesses to main memory.
So to recap the four features, fewer instruction formats, predominantly single cycle execution, fixed length instructions, and a large register file. All these contribute to the speed and simplicity of RSC.
Exactly. The underlying philosophy is that by keeping the hardware simple and fast, any complex operations can be handled by the software through sequences of these simpler instructions.
Interesting. Let's shift our focus now to networking and take a look at question 3, which is all about circuit switching. Part A asks for a description of this concept.
Think back to the way traditional telephone networks operated. With circuit switching, before any communication can happen, a dedicated end-to-end physical connection or circuit must be established between the two communicating parties.
So setting up a direct pathway is the first crucial step.
Precisely. Once this circuit is established, it's exclusively reserved for the duration of the communication, whether it's a phone call or a data transfer. All data flows continuously along this same predetermined route.
And is this path typically one way, or can data flow in both directions?
Usually, circuit switch connections are bidirectional, allowing both ends to send and receive data simultaneously. This dedicated connection remains active until one of the parties involved decides to terminate it.
Okay, so it's a dedicated path that's established beforehand, stays open for the duration, and allows for a continuous flow of data. I understand. Now, part B asks us to identify one benefit and one drawback of circuit switching.
A significant benefit is the guaranteed bandwidth and the predictability it offers, making it well suited for real-time applications. Because the path is fixed and dedicated, data packets arrive in the order they were sent with minimal variation and delay, which is crucial for things like voice and live video. Additionally, the entire bandwidth of the established circuit is available for use by the communicating parties.
That makes sense. Having a dedicated path ensures consistent performance. Now, what's a key disadvantage of circuit switching?
The main drawback is the potential for inefficiency in resource utilization. Once a circuit is established, that dedicated bandwidth cannot be used by any other communication, even if the original users aren't actively transmitting data at all times, like during pauses in a phone conversation.
Oh, so bandwidth can be wasted if the connection isn't constantly being used.
Exactly. Furthermore, if any single link within that dedicated circuit fails, the entire connection is lost. And there's also the initial setup time required to establish the circuit before any data transmission can even begin.
Right, so we have the advantages of dedicated bandwidth and predictable delivery, but the disadvantages of potential bandwidth wastage and vulnerability to link failures, as well as the initial setup delay.
Precisely. Now, let's move up a level of abstraction in networking and consider question 4, which deals with the interaction of the layers in the TCP/IP protocol stack. Application, transport, internet, and link layers. How do these layers work together to enable communication?
It's all about a layered approach to communication, where each layer provides specific services to the layer directly above it, while relying on the services offered by the layer below. Think of it like data flowing downwards through these layers when you're sending information.
Exactly. Starting at the very top, we have the application layer.
That's where the user interacts with network applications, right? Like your web browser using HTTP or your email client using SMTP.
Correct. The application layer is where the data that you want to send is generated. For instance, when you type a message in your email client, that happens at the application layer.
And then that data gets passed down to the next layer, the transport layer.
Yes. The transport layer, which typically uses protocols like TCP or UDP, takes the data from the application layer. TCP, for example, will break this data down into smaller units called segments. It also adds sequence numbers to these segments so they can be reassembled correctly at the destination and includes port numbers to identify the specific application on the receiving end. It adds its own header containing this control information.
So the transport layer is responsible for managing the end-to-end connection and ensuring reliable data delivery, at least with TCP.
That's a good summary. Then these segments are passed down to the internet layer.
And this is where the IP, the Internet Protocol, comes into play, right?
Absolutely. The internet layer takes the segments from the transport layer and adds its own header. This IP header contains the crucial source and destination IP addresses, which are the logical addresses needed to route the packet across different networks. At this stage, the data unit is usually referred to as a packet.
So the internet layer handles addressing and routing to get the data to the correct destination network. And then it goes down another level.
Down to the link layer. This layer is concerned with the physical transmission of data over a specific type of network connection, such as Ethernet or Wi-Fi. The link layer takes the IP packet and adds its own header and sometimes a trailer, creating what's known as a frame. This frame includes physical addresses, like MAC addresses, which are used to identify the devices on the local network segment for the next hop in the journey.
And the link layer is the one that directly interacts with the computer's network hardware.
Yes, it interfaces directly with the network interface card, NIC, to actually transmit the bits of the frame over the physical medium, whether it's a cable or radio waves. This process of adding headers at each layer as the data moves down the stack is called encapsulation. On the receiving end, this whole process is reversed. At each layer, the corresponding header is stripped off until the original application data is revealed at the destination application layer.
It's like sending a letter through the postal service, where each stage adds its own addressing and handling information. Okay, that makes the interaction between the TCP/IP layers much clearer. Let's now turn our attention to data storage and look at question 5, which is about hashing algorithms for file access. Part A asks us to define what a hashing algorithm is in this context.
Imagine you have a very large file containing numerous records, perhaps customer details, and each record has a unique key, like a customer ID. You want to be able to retrieve a specific customer's record very quickly.
Without having to read through the entire file sequentially.
Exactly. A hashing algorithm in this context is essentially a mathematical function. You input the key field of the record, like that unique customer ID, into this function.
And the algorithm performs some kind of calculation on that key.
Yes, it applies a specific set of operations to the key and produces a result. This result is then used ideally as the direct storage address or location, such as a record number or a block address, where that particular record should be stored or can be found within the file.
So it's like key goes into the hashing algorithm and out comes an address, allowing for direct access to the record.
That's the primary goal. Hashing is a key component of direct access methods used for both random and sequential files, although it's most commonly associated with random access file organization because of this ability to directly locate records.
But what happens if, by chance, two different keys fed into the hashing algorithm produce the same storage address? That seems like a possibility.
It is indeed a possibility, and this situation is called a collision. Part B of the question then asks about methods to handle these collisions.
Right, so when a collision occurs, how do we resolve it and ensure we can still store and retrieve both records?
One common and relatively simple technique is called linear probing, sometimes referred to as open addressing. If the calculated address is already occupied by another record, a collision has occurred, you simply check the next available storage location. If that's also occupied, you check the one after that, and so on, until you find an empty slot nearby where you can store the new record.
So it's like looking for the next available parking spot in a row. Is there another common way to deal with collisions?
Yes, another widely used method involves employing an overflow area. This is a separate section of the storage space that is specifically reserved for records that have collided with records in their primary hashed locations. When a collision occurs at a particular address, say address X, the new record is placed in the overflow area. Then at the original location X, you might store a pointer or a link that indicates the actual location of the collided record within the overflow area. Sometimes, if multiple records hash to the same initial spot, they might be linked together in a chain within this overflow area.
So you either look for the next immediate free slot, or you place the colliding record in a designated overflow section and leave a pointer back to it from the original hashed address. Got it. Now let's switch gears and talk about data types. Question 6 focuses on the set data type. Part A asks for a description of what a set is.
Okay, a set is a user-defined composite data type. By composite, we mean that it's a data structure that can hold multiple individual elements, similar to an array or a list.
But what distinguishes a set from these other composite data types?
There are a few key differences. First and foremost, the elements within a set are unordered. Their position within the set doesn't carry any significance. Second, all the elements contained within a specific set must be of the same base data type. For example, you could have a set of integers or a set of characters, but not a set containing a mix of both without some specific handling. Third, and this is a very important characteristic, sets contain only unique elements. Duplicate values are automatically discarded. A set can only hold one instance of each distinct element.
Unordered elements of the same type and only unique elements allowed. That sounds very much like the mathematical concept of a set.
Exactly. And because of this strong resemblance to mathematical sets, you can perform standard set theory operations on them, such as intersection, finding the elements common to two sets, union, combining all elements from two sets, difference, finding elements present in one set but not another, and so on.
Okay, that makes sense. Now, part B of question 6 asks us to write pseudocode to first declare a set type called symbol set that will hold characters, and then to define a variable named operators of this symbol set type and initialize it with the characters plus, dash, and 8.
Right. First, we need to define the type itself. In pseudocode, this might look something like type symbol set equals set of char. This statement essentially creates a blueprint or a new data type named symbol set, which is specified as a set that will contain elements of the character data type.
Type set of char. Got it. And now to declare the variable operators of this newly defined type.
We would typically use a keyword like define or declare, followed by the variable name and then its type. So it'd be define operators as symbol set. This declares that the variable named operators is of the data type symbol set, which we just defined as a set of characters. Finally, to initialize it with the given characters, we would assign the set of these characters to the operators variable. In pseudocode, this is often represented using curly braces to enclose the elements of the set. Operators equals plus a code, rot.
So the complete pseudocode would be type symbol set equals set of char, followed by define operators as symbol set, and then operators equals plus C and A. That seems straightforward enough. Let's move on to the realm of logic with question 7, which involves Boolean logic and Karnaugh maps. Always a bit of fun.
Indeed. Part A of question 7 asks us to write a Boolean expression in sum of products form derived from a given truth table. For the sake of example, let's imagine we have a truth table with 3 input variables, A, B, and C, and a single output variable, T.
Okay, so how do we go from the truth table to the sum of products expression?
The process involves looking at every row in the truth. Oh yeah, let's hear it.
Actually, there are 4 inputs, not 3. It is A, B, C, and D, and the output is T.
Thank you for pointing that out. It's crucial to get the details right. Yes, the truth table in question 7 indeed has 4 input variables, A, B, C, and D, leading to an output T. My apologies for the slip up.
Okay, so with 4 input variables, a truth table will have 2 to the power of 4, which is 16 rows, representing all the possible combinations of the inputs. And for each of these combinations, we'll have a corresponding output value for T.
Exactly. And to write the Boolean expression in sum of products form, we focus on the rows of the truth table where the output T is 1. For each such row, we create an A in D term, a product, consisting of all the input variables. If a variable has a value of 0 in that row, we use its complement, e.g. A, and if it has a value of 1, we use the variable itself, e.g. A.
Right, so each row where t is 1 gives us a minterm. For example, if in one row we have a 0, b was 0, and d were 0, and d equals 1, the corresponding product term would be a, b, c, c, d.
Precisely. Once we have identified all the rows where t equal 1 and written down their corresponding product terms, the final sum of products expression is obtained by ORing together all these minterms. So it'll be a sum of several AND terms.
All right, that makes more sense with 4 inputs. Thanks for the correction. Now, part B of question 7 asks us to complete a Karnaugh map, often abbreviated as K-map, based on the same truth table with 4 variables A, B, C, and D.
A Karnaugh map is essentially a visual tool, a specific way of organizing the information from a truth table. With 4 input variables, the K-map is typically a 4x4 grid of cells, where each cell corresponds to a unique combination of the input variables A, B, C, and D.
And the input variables are arranged along the sides of the map, right?
Yes, the combinations of A and B are usually arranged along one side, say the rows, and the combinations of C and D along the other side, the columns. Crucially, this arrangement uses a gray code ordering. For 2 variables, the gray code sequence is 00, 01, 11, 10. This ordering ensures that only 1 bit changes between any 2 adjacent cells, whether they are horizontally or vertically adjacent, and even the cells at the edges of the map are considered adjacent. They wrap around.
So it's like taking our 16 rows from the truth table and arranging them in this 4x4 grid according to the gray code sequence of the input variables.
Exactly. Once the grid is set up, you take the output value, 0 or 1, from each row of your truth table and transfer it into the corresponding cell on the K-map based on the combination of A, B, C, and D that the cell represents.
So it's a visual representation that keeps logically adjacent input combinations physically adjacent on the map. This sets us up for part of the question, drawing leaps around groups of ones on the K-map to achieve simplification.
Okay, the looping part of K-maps with 4 variables. The fundamental rules remain the same. First, every loop you draw must enclose a group of adjacent ones. Second, the number of ones within each loop must be a power of 2. 1, 2, 4, 8, or even 16 in the case of a 4-variable map where all outputs are 1. Third, you should always try to make your loops as large as possible because larger loops lead to simpler terms in the resulting Boolean expression as more variables will be eliminated.
And loops can overlap and wrap around the edges, just like in the 3-variable case we initially discussed.
Absolutely. Loops can overlap if it helps to cover more ones in larger power of 2 groups, and you can definitely take advantage of the K-map's wraparound property. For a 4x4 map, the top and bottom rows are considered adjacent, and the leftmost and rightmost columns are also adjacent. Sometimes even the corner cells can be considered adjacent as they can form a group of 4. The goal is to cover all the ones on the map using the fewest number of the largest possible loops.
Got it. Bigger loops of powers of 2, covering all the ones with overlaps and wraparounds allowed. Now, after we've drawn these loops, we move on to part, which asks us to write the simplified sum of products expression based on these loops.
Right, so how do we get the Boolean expression from the loops on a 4-variable K-map? Each loop corresponds to one simplified AND term product. To determine the variables that are part of this term, you look at which variables remain constant across all the cells within that loop.
So for a given loop, if a variable A is 1 in all the cells of the loop, it appears as A in the term. If it's 0 in all cells, it appears as A. If a variable changes its value, is both 0 and 1 within the loop, then that variable is eliminated from the term.
Exactly. You do this for all 4 variables, A, B, C, and D for each loop. Then, once you have the simplified AND term for each loop that covers 1 or more ones, the final simplified sum of products expression is obtained by ORing together all of these AND terms.
Okay, that seems like a systematic way to get a simplified expression from the visual representation of the K-map. And then we have part D, using Boolean algebra to write our answer to part D in its simplest form.
While the K-map method is designed to yield a minimal sum of products expression, applying Boolean algebra afterwards can sometimes lead to an equivalent expression that might be considered simpler in a different way, perhaps by having fewer operations or a more suitable form for implementation using logic gates. You might be able to apply distributive laws, De Morgan's theorems, or other Boolean identities to further manipulate the expression obtained from the K-map.
I see. So the K-map gets us to a minimal sum of products, but Boolean algebra offers additional tools to potentially refine or restructure the expression for practical purposes. All right, let's move on to the topic of memory management with question 8, part A, which asks us to describe segmentation.
Segmentation is a memory management technique used by operating systems. Instead of viewing the computer's memory as one continuous linear address space, segmentation divides a program's logical address space into multiple distinct segments. These segments are of variable sizes.
And these segments typically correspond to the logical structure of the program, like code, data, and stack.
Correct. Once defined, these segments can be loaded into non-continuous locations in physical memory. The system uses a segment map table to translate logical addresses, segment identifier, and offset to physical addresses by looking up the base address and checking the segment's bounds.
Got it. Now, part B of question 8 asks us to explain disk flashing. This occurs in virtual memory systems when there isn't enough RAM to hold the active working sets of running programs, leading to excessive swapping between RAM and the much slower hard disk.
Exactly. The constant loading and unloading of pages results in the system spending most of its time on disk operations, causing a drastic drop in performance and potential unresponsiveness.
Okay, let's shift our focus to object-oriented programming and look at question 9, centered around a pet class. Part A asks why we declare attributes as private. This is a key aspect of encapsulation, protecting the internal data of an object.
By making attributes private, access and modification are controlled through public methods, allowing the class to enforce data integrity and hide implementation details for better maintainability and flexibility.
Part B then asks us to complete a class diagram for a pet class, including private attributes like pet name and owner name, and public methods such as a constructor, set petted, set date registered, get pet name, and get owner telephone, specifying parameters and return types. This visually represents the class's interface. Let's now move to question 10, dealing with syntax diagrams and Backus-Naur form, BNF.
These are formal ways to define the grammar of a language. Part A asked us to write BNF for given syntax diagrams for operator, label, and equation. For example, operator.a plus a.
And for part B, we had to write the BNF for a password that starts with a letter or symbol, followed by a digit and ending with one or two symbols. We defined intermediate symbols first and last to represent the start and end parts, leading to passwords first digit last.
Precisely. It's a concise way to define the structure of valid passwords according to the given rules.
All right, we've reached the final question. Question 11, about binary trees and their representation using linked lists and arrows.
Part A asks about the linked list representation. Each node in the linked list holds the data, a left pointer and a right pointer. A value of -1 for a pointer indicates no child, a null pointer. A root B tree points to the top of the tree, allowing traversal.
That wraps up our detailed look at these questions. I hope you found this in-depth discussion helpful.
Absolutely. We discovered a wide range of topics today. Thank you for your engagement and for helping us clarify the details, especially regarding the truth table.
We really appreciate you joining us and contributing to the conversation. Until our next session, keep exploring the fascinating world of computer science.